All right, we are going to start week 2, chapter 2. And in week 2, chapter 2, we're going to talk about the chemical foundations of life, or otherwise, we're going to talk about how chemistry is important to life. And you might be thinking, why are we talking about chemistry and biology? Maybe you've already taken chemistry. Maybe you specifically took biology to avoid chemistry. But we have to study the basics of chemistry when we're studying introductory biology because all living things are made up of atoms, and atoms make up the molecules that are important to life. They make up the proteins that help to build the structures. So when we study biology, we have to study some chemistry because understanding how atoms and molecules work help us understand how processes work. So for instance, if I understand what an ion is, and I can take that understanding and apply it to cell transport. So what is allowed to cross the cell membrane? How does it cross the cell membrane? And if I understand how things cross cell membranes, then I understand processes like digestion, or I can understand how organs like kidneys function. So understanding introductory chemistry, basic chemistry at this level helps us better understand the living world, helps us understand how organisms function. And what we find when we study biology is that it's not interdependent from chemistry or physics. We can't compartmentalize this. An understanding of chemistry helps us understand those life functions. An understanding of physics helps us understand structures and how they allow us to function. So, how does the shape of a bone allow for the movement of a hand? How does the torpedo shape of a seal or a dolphin allow it to move through water better? So, understanding other sciences helps us to better understand the science we're currently studying, which is chemistry. And when we talk about elements and living organisms, there are 6 elements that are essential to life. And they're extremely abundant in those living organisms. We have carbon, hydrogen, oxygen, nitrogen, phosphate, and sulfur. So phosphorus and sulfur. So those elements are extremely important to life. They help to build the macromolecules that living systems use in order to function. So for instance, if you're talking about carbohydrates, carbohydrates are made up of the elements carbon, hydrogen, and oxygen. That's it. That's the only thing that makes up carbohydrates is those 3 elements. If you're talking about lipids and fats, they are made up of carbon, hydrogen, and oxygen. If we want to start talking about proteins, we're going to add nitrogen into the mix. So elements are extremely important in understanding the building blocks that allow for life to occur. And you can see that the distribution of elements within life is different from the distribution of elements within the atmosphere or the Earth's crust. So humans are mainly made up of oxygen. And like if you look at the atmosphere, is mainly made up of nitrogen. And then the Earth's crust is mainly made up of oxygen. So we're just going to spend some time reviewing the basics. If you remember from physical science way back in high school, matter is something that occupies space and has mass. And we organize that matter, or we categorize it, you might say, by identifying elements. When we talk about elements, not elephants, elements, we're talking about particular forms of matter that are only made up of one kind of element. So you're talking about a group or a category of matter that is made up of atoms that are all composed the exact same way. All of these elements, so for instance, if we're talking about oxygen, all oxygen atoms have specific properties that allow it to interact with other atoms and other elements to make molecules and compounds. 92 of the elements that we know of occur in nature, so they're easily found. Now, there are synthetic elements. There are elements that are seen only for a brief amount of time before they'll radioactively decay, but 92 of the known elements are found in nature. And when we look at our 6 elements from this page right here, 4 of them are found in all living organisms. So that means that phosphate and sulfur aren't found in all living organisms. So even though they're important to life. There are some life forms out there that don't use phosphate or don't use sulfur. When we talk about elements, we identify atoms. And atoms are that smallest unit of matter that contains a physical property of an element. So if you go smaller than an atom, you got your atom is made up your nucleus, which is your protons, and then you've got your neutrons, and they're in the center, and then surrounding that are electrons. If you go smaller than an atom, say, let's only talk about electrons, that no longer contains the property of an element. If we go smaller than an atom and only focus on electrons, then we're now only looking at electron properties. We're no longer looking at hydrogen properties or oxygen properties. We're only looking at electron properties. So if you go smaller than an atom, you lose the chemical property of the element. So the atom is that smallest unit that maintains the property of the particular element that it is. Atoms, like we just drew out here, have protons and neutrons in the nucleus, and then surrounding the nucleus are our electrons. The electrons are found in what's called the electron cloud, and the electron cloud contains electrons which move about the nucleus. Now, what we know is that electrons move around the nucleus, and they move around the nucleus kind of in an undefined path. It's more like we know that in this general area right here, we're going to find 2 electrons. Now, those aren't going to necessarily orbit like the Earth orbits the sun, but we know that in this general area, we're going to find 2 electrons outside of the nucleus. And we know that in this general area right here, we're going to find 8 electrons. And we know that if we move out even further, in this general area out here, we're going to be able to find at least 16 electrons. So we find that the electrons move kind of crazy, but we generally know where those electrons can be found. Where did I go? There we are. So we call that the electron cloud, the area in which the electrons surround the nucleus and move about the nucleus. Isotopes are atoms of a particular element that have different numbers of neutrons. Elements are identified. Elements are identified by the proton number. So, for instance, all hydrogen atoms have 1 proton. Okay? All helium atoms have 2 protons. So the proton number is kind of like the hello, my name is oxygen. Now, the proton number, if the proton number changes, it changes the element itself. So if I change hydrogen's proton number from 1 to 2, I no longer have hydrogen, I now have helium. But the electron numbers within an atom can change, and the neutron numbers within an atom can change. If I have an atom of a particular element with different numbers of neutrons, I have an isotope. Isotopes can have many different functions. We use isotopes, especially radioactive isotopes, in imaging. So if you've ever had to take iodine injection before an imaging test, that would be an example of a radioactive isotope that's used to help identify issues and diseases. Atoms are held together by chemical bonds. The reasons that atoms bond is to increase stability. Atoms want to have what is called a full valence shell. All right, a full valence shell. And I'm going to add that picture that we just looked at back in because it's going to help us understand. All right, so like I said earlier, we know that in like this particular area, you're going to find up 2 electrons. In this particular area, you can find up to 8 electrons. All right. And the outermost shell is called the valence shell. So if I'm talking about helium that only has 2 protons, we're going to assume that it has 2 electrons. This would be helium's, this right here would be helium's valence shell. All right. In this case, this one right here is the valence shell. Now, atoms want to have full valence shells or 8 electrons in that valence shell. And that makes atoms happy. That is an atom's safe space. It's going to reduce the activity of the atom. If the atom's valence shell, outermost shell, is not full or does not have 8, it's going to bond in order to be there. So atoms will bond to increase stability, and stability is reached when we reach that full valence electron shell or when we reach 8 in that valence electron shell. So when we talk about that, we're talking about the movement of electrons. So electrons are always moving, and when they are moving to their lowest state, they become less reactive. So when atoms are bonding together, they're literally moving those electrons to a more stable state. So the first electron shell will have 2 electrons. All right. So let's call this our nucleus right here. I'll make it a different color. Our nucleus right there. That first valence shell or first electron shell will contain 2 electrons. And if you're talking about atoms such as helium, that makes a full valence shell for helium. Helium is a not very reactive element. When you look at the periodic table, helium is in the group called the noble gases. These elements right here all have either full or 8 in their outer valence shell. Our next valence shell level is 8. So the second shell can hold up to 8 electrons. All right. The third shell can hold up to 18 electrons. And I need to make a correction. I think I said 16 earlier. But you can hold up to 18 electrons in this third valence shell. Now, if there are 18 electrons in this third valence shell, then the atom is stable. It's not going to be very reactive. If there are 8 electrons in this third valence shell, then the atom will be stable. It won't be very reactive. But if there are 17 electrons here, that means there's space for one more. And that atom that has 17 in this third shell is going to be reactive. It's going to want to attempt to fill that valence shell, and it's going to do that by bonding to another atom. All right, so chemical bonds allow for the combination of elements, and the whole goal of that chemical bond is to fill the valence shell. Okay, we want stability. So atoms want stability in their lives just like we want stability in our lives, and they do that through bonding. So there are 3 types of chemical bonds that we're going to talk about, and we're rearranging atoms. So we're not changing the atom themselves. However, when we have a chemical bond, it can change the way the atom behaves. So, for instance, sodium. Where is sodium? Sodium, right here. Sodium in its pure elemental form is a highly reactive metal. Extremely reactive metal. It has to be stored under water. It cannot be under oil. It cannot be exposed to air. It will react. It cannot be exposed to water. It will react. So it has to be stored in pure elemental form in oil. But when it's bonded with chloride right here, it becomes NaCl. And we like it so much we put it on our French fries because it is salt. So elements in their elemental form can behave differently when bonded to other elements. All right. Chlorine in its elemental form is a poisonous gas, but when bonded to sodium, it becomes salt. So chemical bonds change the reactivity of those atoms and give you molecules that can have different properties and different actions than what each element in the molecule does on its own. So 3 types of bonds we're going to talk about are covalent bonds, ionic bonds, and hydrogen bonds. During the chemical reaction or during the formation of a bond, we are rearranging the molecular or ionic structure of the substance. So we are moving electrons. We are rearranging the way they interact. New substances are formed. Those substances will have properties that are different, most likely, from the elemental properties of the elements that are making up the substances. When we go through a chemical reaction, we are rearranging the atoms or bonds and giving new results. When we talk about a chemical reaction, we have reactants that will come together and give us products. Products. Nope, I spelled that wrong, didn't I? Okay, so what we are saying that is that molecule AB plus molecule CD can and will behave differently than molecule AD and molecule BC. All right, so we are rearranging the atoms and the bonds, and they're giving us different results. So this is an example of a chemical reaction. So what we see here are the elements hydrogen, right here, hydrogen, and the elements oxygen. We have 2 hydrogen and 1 oxygen, and it goes through a chemical reaction and gives us a product of H2O. So hydrogen and oxygen are our reactants, and water is our product. And what I want you to note here is this. This is hydrogen's electron, and this is hydrogen's electron. Hydrogen is in this first valence shell. And if you remember, the first valence shell holds 2. So our valence shells are, remember, 2, and then it's 8, and then it's 18. Okay, so this first valence shell is not full. Hydrogen has 1 electron. It wants 2 electrons. And if we look at oxygen, oxygen has 2 electrons here. Wrote that wrong. 2 electrons here. And then it has 1, 2, 3, 4, 5, 6 electrons there. So in our second shell, so this is our first shell, in our second shell, we want 8, but we only have 6. So oxygen here is not stable. It wants 8. It needs 2. So what it does is it shares electrons with hydrogen. So hydrogen is sharing its electron with oxygen. Oxygen is sharing its electron with hydrogen. So now hydrogen has 2 electrons circling its nucleus, right? And oxygen gets hydrogen's electrons. Well, oxygen does it twice. So this hydrogen now has 2 electrons circling the nucleus. And this oxygen will have 8 electrons in this valence shell now. So what they've done is they've chemically bonded together, and that's allowed each atom in the compound to share electrons and fill their valence shells so that they are content. When we talk about chemistry, there's a lot of notation. So understanding that notation helps us understand what's going on. And the notation allows us to know things like, for instance, if you're talking about symbols, allows us to know that the element is hydrogen. Okay, and this symbol, carbon. So chemical notation, chemistry notation, diagrams, things like that helps us understand what we're looking at. It understands what this molecule is made up of. These dots right here that we're looking at in this diagram right there are representing electron pairs that are being shared. So they are literally representing bonds that are holding the hydrogens to the carbon. All right, so what else can we learn from this diagram right here? We have one carbon atom, and we have 1, 2, 3, 4 hydrogens. And now we have a molecular formula where we have CH4, which is methane. So diagrams and notations and things like that can help us explain what's going on. So the diagram below shares electrons being shared, which is a type of chemical bond between 4 hydrogens and a carbon. So bonds can also be represented by lines. So if we look over here, our bonds are represented by our dots. So they are literally showing those paired electrons being shared. But bonds can also be represented by lines, and you will see them most commonly represented by lines here. All right. If we are looking at what's called a single covalent bond, we're going to talk about covalent bonds in a second, but basically one line represents a single covalent bond. If there was to be double lines like this, that is a double covalent bond. So 2 lines is double, 1 line is single, 3 lines is triple. So if it looked like that, then you would see that it's a triple covalent bond. Now carbon has 4 electrons in its outer energy shell, in its valence shell. So carbon has 2 electrons in the first shell, and it has 4 electrons in the second shell. But this shell right here, if you remember, if we go back, this shell right here wants 8. So carbon has 4 electrons, but it wants 8 electrons. So that means that carbon holds 4 bonds, and it will bond with 4 things in order to get 4 electrons in order to get that complete outer energy level. Sometimes carbon will have double bonds. So like if you had a double bond right here, you would not see that because the carbon will only hold 4 bonds. 1, 2, 3, 4, right? If you had a triple bond, so let's say we have a triple bond right here, carbon will only hold 4 bonds. So that's 1, 2, let's call this one 3, and it would not have these 3. Because carbon will only hold 4 because it's trying to get to 8. It's trying to take the 4 that it already has and get to 8. All right. There's several different ways and methods to represent molecules and symbols in the bonds that it has. Molecular formula is basically just telling you the elements and the proportion that you see them in. So we, in this formula, have 1 nitrogen and 3 hydrogens, right? The structural formula will show you your bonds. So you have nitrogen here. It has 1 single bond to a hydrogen, a single bond to a hydrogen, a single bond to a hydrogen, and then 2 free electrons, right? So this is the same molecule. We're just showing you the structural form. The ball and stick model shows you how that might look. Shows you the bonds and how the elements might look bonded together. And the space filling model just kind of gives you that, both of these do actually, a 3D idea of what those look like. What you see in the ball and stick model are the bonds. You don't necessarily see bonds within the space filling model. All right, so let's get down and dirty and start talking about covalent bonds. When we talk about covalent bonds, we are sharing, right? Covalent bonds is sharing, just like co. So if you're talking about co-captains, co-captains are sharing the responsibility of captains. So in covalent bonding, we're sharing electrons and we're trying to fill our outer energy level. So we're trying to fill that valence shell. In a single covalent bonds, 2 pairs are shared. In a double covalent bond, 4 are shared, 4 electrons are shared. In a triple covalent bond, 6 electrons are shared. When we're talking about a nonpolar covalent bond, we're saying that electrons are shared equally. So if we look at our methane with our CH4, those electrons are being shared equally all the way around that carbon. So that is nonpolar. Polar covalent bonds, electrons are not shared equally. So they're not sharing that as well as this molecule is. And our most common example for this is going to be water, where the electrons are being pulled towards that oxygen molecule. So that makes the oxygen more negative and the hydrogen's more positive. So let's talk more about water and covalent bonding. Hydrogen has 1 electron. The outer energy level is not full. So hydrogen has only 1 electron, right? Oxygen has 8. So oxygen will have 2 electrons in the first level and 6 electrons in the second level. The second level wants 8. But oxygen only has 6. So we have an unfilled valence electron level here. So the 2 electrons of hydrogen fill the oxygen's valence level right there. So that oxygen gets +1, +1, and we get to 8. Now, oxygen is also sharing electrons with hydrogen. So hydrogen gets +1. It has 1, gets 1 from oxygen. It becomes full with 2. This hydrogen has 1, gets 1 from oxygen. It becomes full with 2. So oxygen's electrons help to fill out hydrogen's outer energy shell, and hydrogen's electrons help to fill out oxygen's outer energy shell. Now, we're not giving these electrons away. We're sharing them. So let's say that I am a little blue electron and I am going around oxygen. I am also maybe going around hydrogen. Okay? So I am literally orbiting all the way around this molecule. Okay? The law of conservation of matter says that atoms and particles are not lost. We're just rearranging them. So we're saying that sometimes that electron is going around hydrogen, and sometimes that electron is going around oxygen. Hydrogen's not losing an electron. Oxygen's not losing an electron. We're just rearranging where those electrons are at different periods of time. All right, and you can see this diagram that we looked at earlier. Now, this is an example of a non-polar covalent bond. Okay, so we are sharing, and we are sharing unequal. Okay, we are unequally sharing. Wait, that's an example of a polar covalent bond. Did I not put that in there? There we go. Polar covalent bond. Water is an example of a forget I even said this. Let's move on. Water is an example of a polar covalent bond. So the electrons are shared unequally between those bonding atoms. It has to do with electronegativity, or the measure of a tendency of an atom to attract bonding electrons. And I found a periodic table to help us understand this a little bit more. It's this one right here. So some electrons or some elements are more electronegative than other elements. So for instance, the most electronegative element on the periodic table is fluorine. The least electronegative element on the periodic table is cesium. Now, the closer atoms are to electronegativity, the more likely they're going to share electrons equally. The further apart they are with electronegativity, the less likely they are going to share electrons equally. So when we talk about water, water's a yellow, oxygen or hydrogen's a yellow, oxygen's a red. They are far apart in electronegativity, and so they're not going to share electrons equally. If we go back to our CH4, our methane, carbon is a 2.5, hydrogen is a 1. So both carbon and hydrogen are about the same electronegativity, so they're going to share those electrons equally. So when an atom with greater negativity bonds to an atom with less negativity, the electrons are going to be pulled towards the most electronegative atom. So if we go back over here and erase all this mess that I wrote, when water, the hydrogens bond with oxygen, oxygen has the greater electronegativity. So the electrons are going to be pulled towards that oxygen atom. And that gives what's called polarity. And a polarity is just a difference in charge at either end of a molecule. So if you look at this little magnet right here, you can see that one side is plus and the other side is negative. So we know that magnets can have polarity where one side has a different charge than the other side. And that's exactly how a water molecule is going to work. They're going to start to work like molecular magnets, where one side is positive and the other side is negative. All right, and they're going to be attracted together to each other like molecular magnets. So oxygen has the greater electronegativity, like we saw in our periodic table. So the electrons of the bonding hydrogen are being pulled towards that water molecule. So oxygen attracts the electrons more strongly than hydrogen. So when you look at it in a diagram form, this is our hydrogen here. This is our oxygen here. When we're sharing electrons, the electrons are going to be pulled towards the oxygen nucleus. All right. So we're going to share them, but they're going to go around the hydrogens, but they're going to mainly be in the area towards the oxygen nucleus. All right. So the nucleus of the hydrogen is positive. All right. So that's going to make this end of the water molecule more positive. Now the oxygen over here, it has all of these electrons moving around its nucleus. It has a lot more electrons than hydrogen does. So you see more electrons around the oxygen, so the oxygen end is going to have a negative charge. So if we were to compare this to our magnet, this would be our negative side and this would be our positive side. And these molecules are going to interact like magnets with each other. Okay, so let's go back and talk about nonpolar since I got my wires crossed. Nonpolar covalent bonding is when electrons are shared equally. So covalent is sharing. Nonpolar means equal. So these two happy hydrogens right here are playing tug of war, and neither one of them are winning. So neither one of them are getting more electrons than the other. So they are equal in the amount of pulling that they're doing. So they're not being pulled more one way or the other. It's being pulled equally. And here's how you can see this. Like, we're going to explain it like we explained water. We have our hydrogen molecules, and they each have, right here, one electron. All right? So they need 2 electrons in the valence to be full. So what they do is they share. This electron is going to go around, and it's going to go this way. All right? Same way with this electron. It's going to go around, and it's going to go this way. So these electrons are going to be circulating or orbiting or moving around both nuclei. All right? So because when you look at our, our electronegativity periodic table, hydrogen, when you're bonding to itself, it's obviously going to have the same amount of electronegativity. There's no huge difference like there is with water. So we're going to have the same charge around both nuclei. So they're going to have an equal charge around both nuclei. You don't have the magnetic effect like you do with, or the polar effect like you do with water. All right, so this is some examples. This one, first one right here is water. Water is going to have more electrons. Ooh, that is hard to read. More electrons towards the oxygen end, so it's going to be negative. It's going to have more positive end towards the hydrogens. So since we have a more positive end and a more negative end, water is polar. All right. Since we are sharing electrons, it is covalent. Methane, all right, has a single carbon, and it's basically surrounded on all sides by hydrogen. So it is literally, a carbon star surrounded by a hydrogen posse. So those hydrogens are completely encasing the carbon, and so those hydrogens all have the same electronegativity, so it's going to be equal around it, and it will be nonpolar. So equal charges around a molecule is nonpolar, and then when you have a more positive versus a more negative end, you're going to have polar. All right. This is going to be CO2. All right. Carbon and oxygen. Let's look at our electronegativity chart. Carbon and oxygen, all right, are a little farther apart on the electronegativity chart, but they are much closer together than water or hydrogen and oxygen. Sorry, that's kind of hard to read. They are much closer together than hydrogen and oxygen. But when we look at this molecule, the carbon right here is surrounded by the oxygen. So even though they're further apart on the electronegativity periodic table, even though they have different charges, because that carbon has an equal charge surrounding it, all the way around it, right? Because it's the same, it's going to be nonpolar. All right, so polar, you have a negative end and positive ends. You have poles. Nonpolar methane is going to be positive all the way around. So it's going to be the same all the way around. All the way around that molecule. So that is nonpolar. Okay. Oil and water do not mix. Water is, as we've learned, polar. All right. So oil is a lipid, and lipids are made of carbon, hydrogen, and oxygen, right? So what happens, though, is that lipids are made up of carbons that are strung together, and they are surrounded by hydrogens. That's an H right there. So even though they are composed of different elements, they still have the hydrogen surrounding them all. And because it has that same charge all the way around it, it is nonpolar. So oil is nonpolar. Water is polar. When we talk about mixing things, like dissolves like. All right, so that's the same as saying polar dissolves polar. And nonpolar dissolves nonpolar. Ugh. Writing on an iPad is harder than you would think. Non-polar, especially when you have bad handwriting in the first place. So, if polar dissolves polar and nonpolar dissolves nonpolar, and we have water and oil, That is polar trying to dissolve nonpolar. And that is not like dissolves like. That's like dissolving, trying to dissolve something is different. So different and different don't mix. So water and oil don't mix because water is polar and oil is nonpolar. All right, so that's covalent bonding. Covalent is sharing. So let's just really quick do some takeaways. Covalent, shared electrons. If they're equally shared, they are nonpolar. Oops, not polar, polar. If they are unequally shared, they are polar. So in a nutshell, covalent bonding. All right, so let's move on to ionic bonding. Ionic bonding is when electrons are not shared, they are given and received. Okay, so given and received. So the differences in electronegativity actually pulls off the electron of one atom and then attaches it to the electron of another atom. So in our funny little cartoon here, we have one atom that is going to give an electron to another atom. So you have a giver and a receiver. Atoms that lose an electron take on a positive charge. So if I have, let's say I'm talking about oxygen, and oxygen has 8 protons and 8 electrons. If I lose an electron, I now have 7 electrons. So I now have more positives than I do negatives. So atoms that lose an electron become positive. If I gain, there's a typo, an electron, then I take on a negative charge. So let's just do this again. If I gain an electron, I become negative. Oxygen has 8 protons and 8 electrons. If I add an electron, I now have 9 electrons. So I have one more negative charge than I have positive charge. So my overall charge is negative. When we have positive and negatively charged particles, we have ions. Now, ions are extremely important in living substances. So we talk about ions all the time in biology. If I am a negatively charged ion, I am called an anion. So this is the example of an anion. If I am a positively charged ion, I am a cation. And so this is the example of a cation. These oppositely charged ions are attracted to each other and they will bond. And when those are attracted and bonded together, you have ionic compounds. Now, how do we remember anion and cation? So you may have noticed as I was pulling up my periodic tables and diagrams and such, this little cartoon right here. I showed this in my class and my kids love it. Cations are positively charged. All right, so cations are positively charged. Another way that I remember it, and I am a firm believer in whatever way you can get it to stick in your head, by golly, do it. All right, whether that's a Henri mnemonic or a song, or I have students in my anatomy classes that have to touch the parts of their body that they're talking about, which can sometimes get awkward. But however you can get it to stick in your head, do it. So the way that I remember anion versus cation is anion, some reason, looks to me like onion. Right? So that A is very similar to me to onion. And I do not like onions at all. I don't like them at all. They're disgusting. So that's a negative for me. All right. Cations reminds me of cats. Cats are fun. And so that's a positive for me. So however you can get it to stick in your head, by golly, do it. But ions are important because They serve as messengers for the cell. So for instance, if you're talking about sodium ions and potassium ions, we can't have muscle contraction without either one of those. Muscle contraction is essential for movement, whether you're talking about moving your skeleton or you're moving materials down your digestive tract. If you don't have muscle contraction, you don't have movement. And without ions, you don't have muscle contraction. So ions are important. And so this is an example of the formation of an ion. So sodium has 1 electron in its valence electron shell. So it is not in a stable place, right? Because it's not full or it's not 8. Chlorine has 7 electrons in its valence electron shell. It is not stable. It doesn't have a full valence electron shell, and that valence electron number is not 8. So what happens is the chlorine will actually pull that extra electron from sodium into its electron cloud. And so this electron leaves. It's not shared, it actually leaves and becomes part of the chlorine electron cloud. So now we have 8 and we're happy, and now we are full and we are happy. So we are content, we are stable. But now this atom right here, if you notice, they show it right here, it has an negative charge because it has 1 more electron than it does protons. And this atom right here, if you notice, has a positive charge because it has 1 more proton than it does electron. And if we learned anything about dating and relationships and bonding in life, opposites attract just like they do in chemistry. So opposite charges here, positive and negative, attract, and they will form what's called an ionic bond. All right, so those opposites attracting together, those opposite ions being pulled together, form an ionic bond. And in this case, we're talking about the ionic bond that makes NaCl, or salt. All right, so this diagram just basically demonstrates everything that we just talked about. That extra electron from sodium transfers to chlorine. Chlorine becomes negative, sodium becomes positive, opposites attract, and we have salt crystals that form. All right. The final type of bonding that we're going, let's quick recap. Ionic bonding. Ions form. Ooh, that's weird. Ions, there we go, form. Cations are attracted to anions. So cations, if you remember, we like cats are positive, and anions, I hate onions, are negative, are attracted to each other. And so opposite charged, that's a weird S, opposite charged ions bond. All right. Our last type of bond that we're going to talk about is hydrogen bonding. Hydrogen bonding is not necessarily bonding, is not bonding to build molecules. Hydrogen bonding holds separate molecules together. Okay? We are not building. We are holding separate molecules together. So it is a weak bond between covalently bonded molecules. So the hydrogen of one molecule and an electronegative portion of another molecule, usually oxygen or nitrogen, are attracted to each other. All right? These are intermolecular. So molecule 1 is attracted to molecule 2. All right? Usually you see these as indicated by dotted lines. So let's change this line. So this attraction, is indicated by dotted lines. So let's look at an illustration here. We have in this illustration a bunch of water molecules, all right? And if you remember, water molecules are covalently bonded together. So you have oxygens that are covalently bonded to hydrogens. Your oxygens are negative, your hydrogen ends are positive, right? Oxygen end is negative, you have your covalent bonds, hydrogen ends are positive. You can think of it like a sad Mickey Mouse, right? So there's your Mickey Mouse. Your face or your nose is your oxygen, and then your ears are your hydrogens. And it's a sad Mickey Mouse. Maybe Disney World's closed today, or maybe Minnie Mouse is on vacation and he's getting lonely. Who knows? But he's sad. So the oxygen end of our Mickey Mouse is negative, and the ears, they're still pointed up, and he's still got pointy ears or rounded ears, whatever. But he's got a sad face and he's got happy ears. All right. So our Mickey Mouse has a sad face and happy ears. Let me redraw that. Oh, stupid. Here we go. He has a sad face and happy ears. So whenever you look at your water molecules, oxygens are negative, hydrogens are positive. They are covalently bonded together. Covalent bonds are typically illustrated by lines depending on the number of electrons shared. All right. So the positive hydrogen end of one molecule is attracted to the negative oxygen end of another molecule. So the positive hydrogen end of one molecule is attracted to the negative oxygen end of another molecule. Now, these attractions between molecules that you're seeing right here, we're pointing at right here, these attractions are not stable. So these attractions are constantly being formed and reformed. So that gives water a lot of really interesting properties. So illustrating again, we have our oxygen right here, our hydrogens. Oxygen is negative, hydrogen has a positive charge, slightly positive charge. So the negative oxygen right here, negative oxygen, is attracted to the positive hydrogen right here through this hydrogen bond. Okay, so let's think about our magnets. I don't know if you've ever had a chance to play with magnets. I hope so, because they're kind of fun to play with. But let's think about our magnets. What happens when you have magnets set up like this? This is our Dora the Explorer moment. I'm just going to pause and let you think. All right, what happens when you have magnets set up like this? When you have magnets put together so that opposite or similar charges are together, these are both negatives, these are actually going to push away from each other. So this one will be pushed this direction, and this one will be pushed that direction, because magnets don't like to set up like that. Now, if we have magnets down here that are set up like this, all right, what's going to happen in this case? In this case, the negative end will be pulled towards the positive end, and the positive end will be pulled, that is a horrible arrow, towards the negative end. So this magnet will go this direction, and this magnet will go this direction, because opposites attract. And that's exactly what's happening with our water molecules. This opposite charge hydrogen or oxygen atom is attracted to the positively charged hydrogen atom, and that attraction forms that hydrogen bond. All right, this gives water a lot of properties. I joke that when we're talking about water, when all else fails, answer hydrogen bonding, because so many properties of water are the result of hydrogen bonding. So for instance, it makes it a very versatile molecule. And so let's talk about density. Water is more dense as a liquid and less dense as a solid, which is kind of strange. What happens is during freezing, the hydrogen bonds will kind of stabilize a little bit, and they will hold water molecules at arm's length. So that's a hydrogen, so this needs to be an oxygen, right? So this is a hydrogen, so this needs to be the oxygen end. And so what happens is you form this crystalline structure, right? And the crystal is literally forming crystals, like if you think about snowflakes. The reason that's occurring is because as the temperature of the water decreases, the movement of the molecules between movement of the water molecules slows down, and that allows the hydrogen bonds to stabilize. So it literally holds, those hydrogen bonds will literally hold the water molecules at arm's length, making them less dense than when you're liquid, when those water molecules are tighter and they're able to move past each other. So this is why, for instance, ice will float on the surface of a pond. When it does that, it helps to insulate the water that's below. So let's just think about ice. If the ice were at the bottom of the pool, or bottom of the pond, or the bottom of the lake, the bottom of the stream, then all of the water above it is going to be chilled by that ice, because it's all running over the top of it. But since it's floating on the top, it's forming a layer that insulates the lower part of that pond, or the lower part of that stream. So it kind of helps to maintain that stream's habitat throughout the winter. So this is the water molecules. You can see how they're being held apart and forming what's called a crystalline structure, or a crystal, as opposed to a liquid water molecule that is constantly forming and reforming those hydrogen bonds, so the molecules are able to move past each other. Since it's less dense, it's going to float. Less dense things float. It's going to form a layer on the top of that water system, and the organisms that are living underneath that layer kind of have that insulative quality in their ecosystem to help maintain their environment. Now, is it going to stay warm? No, it's not going to stay warm, but it's maybe just not going to get as cold. This is another example of crystalline structure, and you can see that there's ice floating on the water. Another property of water that is the result of hydrogen bonding, so if all else fails with water, hydrogen bonding, is the fact that water is almost a universal solvent. That means it dissolves a lot. It dissolves a lot. Not everything, but it dissolves a lot. So we can form solutions with that. So a solution is a mixture of more than two kinds of molecules, atoms or ions, that is homogeneous, which means the same throughout. And water helps to form those solutions. It is a solvent, which means that it does the dissolving. Solutes are what are being dissolved. Water is nicknamed the universal solvent because it does such a great job at dissolving. So let's talk about solute and solvent real quick. All right, solute is dissolved. Solvent does the dissolving. Okay. Now, my husband loves sweet tea. I'm an unsweet tea person. I'm one of those. But my husband and my daughter actually love sweet tea. So when I am making sweet tea, I am taking water as a solvent, and I am dissolving sugar as a solute. All right? So the sugar is being broke down by that water homogeneously, the same throughout, and I'm forming that solution of that sweet tea. So remember, the solute is being dissolved, the solvent does the dissolving. In this case, we're making salt water. Water is our solvent, and then our solute is salt. So that salt is going to be broken down in that salt water, and it's actually, because salt is ionic, NaCl, that means that we have a positive Na plus a negative Cl make NaCl, right? So we have a positive charge and a negative charge, and we talked about how water is polar, which means it has positive end and negative end. So like dissolves like. We have positives and negatives that can be dissolved by positives and negatives. So when we dissolve salt water, we are literally breaking it into sodium and chlorine ions. Polar water molecule is attracted to the sodium ions and the chloride ions. So what's interesting here is we look at our ions, right? So this is a sodium right here. Oops, sorry. This is sodium. Has a positive charge. Let's do this with a smaller font. Positive charge right there. All right. Now, do you remember the charge of your water molecules? We have, remember, a sad oxygen, sad Mickey, happy ears, right? Sad Mickey, happy ears. Kind of looks like a frog more than it does Mickey right there. But our oxygens are negative. So if you look, you have a positive ion here, and the part of the water molecule that's being attracted to that positive ion is the negative oxygen, right? So opposites attract. In this one, you have a negative chlorine, negative ion here, and the positive end, those positive hydrogens are being attracted. All right. So the water keeps those ions evenly dispersed in solution. It will surround all those ions, forming what's called a hydration shell, and it keeps them apart. So salt water is going to stay salt water until there is energy added to it that is going to cause those chlorines and sodiums to come back together. So if we take that pot of salt water and we put it on the stove, we're adding energy. The water itself becomes water vapor and goes away, and that leaves sodium and ion, gives it sodium and chlorine a chance to come together and come back as salt. All right. So this is another example of some hydration shells where you have your positive sodiums attracted to your negative end of your oxygens, and your negative chlorines attracted to the positive end of your hydrogens. Okay. All right. Another property of water is specific heat. And specific heat is the ability of water to raise the amount of energy that it takes to change the temperature of a substance by 1 degree Celsius. Water will absorb a lot of energy before you can see an increase in temperature. All right. So if you're in an ecosystem that has a lot of water, you're going to see more stable air temperatures because that water will take a lot of the solar energy and absorb it before you see a change in temperatures. So it can reduce the amount of change in temperatures in the ecosystem, and it can release that energy in the environment. So if, for instance, if you live on the coast like San Diego, if you live close to the water, you have pretty constant, pleasant temperatures. That's why people go to San Diego. But if you move inland in California, the further away you get from that ocean, from the Pacific Ocean, the more variation that you have in temperature. So the ability for water to absorb all that heat helps to buffer temperature changes on Earth, and it also helps to buffer temperature changes in living things. So, we as living things are composed of a lot of water, and that water will help to absorb the energy from our bodies as we're working. It's one of the reasons why it's important that we stay hydrated, because it helps to regulate our body temperature. And specific heat all has to do with the collective strength of hydrogen bonds. Remember, hydrogen bonds independently are very weak. They are constantly forming and breaking and reforming. But when you look at the weak hydrogen bonds collectively as a group, they hold together pretty good. Properties of water: cohesion and surface tension. All right, so these are literally the attraction of water molecules to each other and the attraction of water molecules to other substances. So cohesion is the attraction of water molecules to each other, and adhesion is the attraction of water molecules to other things. All right, and together they give us surface tension. So literally what is happening is that the water in this picture, you see the water molecules moving over the swimmer are staying together because of cohesion, and they're staying on the swimmer because of surface tension. You see surface tension in other places where you see droplets beating up maybe on your car window, and that happens because there's a distribution of forces. Here's an example of surface tension. On a spider web, you see the droplets holding together, and that the cohesiveness of the water molecules are pulling the droplets together, and surface tension is holding them together. So what you're seeing is a distribution of force. Remember when I told you that there's physics in biology? Here's some of those physics in biology. The force at the surface is being distributed in 2 directions. The force underneath is being distributed in 3 directions. So it kind of forms, it's not a film, it's not like a plastic wrap, but it acts kind of like that because of the strength of the distribution of forces. If you go down into the middle of the water droplet, that force between those water molecules is being evenly distributed all the way around in all directions. So you don't have that film-like property like you do up here because it's not as evenly distributed as it is on the surface. And that allows things like water striders to walk across. So this water strider, the structure of its leg allows it to have a great contact with the surface of the water, and it's able to distribute its force in a way that it doesn't break through the water and it can walk on top of the water. Beating up is another example we talked about earlier. This is water beating up on a feather. So the water droplet itself, the water molecules are attracted to each other through cohesion, and they're staying together in that bead, in that droplet, because of surface tension. All right. There is a really cool video I don't have time to show you today that I definitely want you to look up. Skip trial. It's called Wringing Out Water on ISIS for Science. It's 3 minutes. It's definitely worth your time, but this lecture is really going to be long as it is. But check it out. Wringing Out Water on ISIS for Science. It's a really cool look at surface tension and cohesion and adhesion in space. So capillary action is a reaction that's caused because of cohesion and adhesion. So the adhesive forces of the water, remember, adhesion is water plus other. Okay, cohesion is water attracted to water. So adhesion is the attraction of the water to the tube. A capillary tube is just a really skinny glass tube. Think of it as like a micro straw, so it's very, very small. And the water will go up the side of that tube because of adhesive forces. So the water, in this case, is attracted to the glass. And then cohesive forces is going to pull the water up the middle. Water is attracted to itself. So you can see capillary action in, you can see a little bit of capillary action in like your McDonald's cup, where you have your cup, right, and your straw, and you can see in that little tiny straw just a little bit of capillary action. You won't see a lot just because of the size of the straw compared to the size of the cup. But basically, your Dr. Pepper is rising up a little bit higher than the surface of the Dr. Pepper in a cup. You see this a little bit of what's going on when you're looking at a graduated cylinder. So if you've ever done a lab where you've had a graduated cylinder, you've seen a little bit of kind of capillary action where you have your cylinder, right? And then you have your water, and it's forming this U shape, which we call the meniscus. So the water that is climbing right there is using adhesion to climb that glass. Remember, when you are measuring water, you are looking at measuring with a graduated cylinder. You are looking at the bottom of the meniscus because you don't want to be deceived by the water that is crawling up the side of the graduated cylinder. All right. Properties of water: hydrophobic and hydrophilic. Hydrophobic is just what it sounds like, where phobia is fear. Hydrophilic is the attraction. So this is a fear. And philic, this Phili, is a love. All right? So we are water fearing and water loving. So life requires molecules that can't be dissolved by water. It's essential. If everything was dissolved by water, we would literally just be walking. Well, we wouldn't be walking. We'd be a puddle. All right? There would be no cell membrane. There would be no skin because everything would be dissolved by water. So we have to have molecules that cannot be dissolved by water. Remember when we talked about like dissolves like? So we have non-polar molecules that are not dissolved by the polar water molecule. Remember, water is, why do I keep forgetting that R? Water is polar. Right? So we have non-polar molecules that build structures like cell membranes that cannot be dissolved by water, that allow us to build those contained areas. Non-polar molecules are Non-polar molecules are hydrophobic. They will not interact with water. So oils and fats, and all non-polar, right? Hydrophilic molecules are molecules that will interact with water. So water is polar, like dissolves like, so polar molecules are hydrophilic. Ions, so positive charges and negative charges. Salt is an example. You remember, you've got your positive sodium and your negative chlorine is an example of a molecule that does interact with water. Water will dissolve hydrophilic. Water will dissolve hydrophilic. Water will not dissolve hydrophobic. Okay, and this is seen in this example where you have an oil spill, and you see the oil down here is staying on the surface of the water. It's not mixing down into it. It's not interacting with the water because oil is non-polar. Oil is hydrophobic. Okay. pH scale is another example of properties of water. A pH scale measures the amount of hydrogen ions and hydroxide ions in solution. And then hydrogen ions. That's an H. Okay. Materials that are acidic have more hydrogen ions. Materials that are basic have more hydroxide ions. All right. It's a logarithmic scale. There's a lot of math that's associated with it, but we're not going to mess with it. But we need to understand that the more acidic a material is, the more hydrogen ions that you have. So let's just really quickly draw a quick and dirty pH scale. All right. So the pH scale runs from 0 to 14. All right. The middle of the pH scale is 7, and 7 is considered neutral. At 7, the amount of hydrogen ions is equal to the amount of hydroxide ions. Water will break down into hydrogen and hydroxide. All right, so water will break down into hydrogen and hydroxide. Water is neutral. A pure water, like not like well water. It's probably got some ions and minerals in it, but pure water. If you are from 0 to 7, you're acidic. So as you move from 0 to 7, hydrogen ions increase, hydroxide ions decrease. 7 to 14 is basic. You may also have heard the term alkaline. All right. As you move from 7 to 14, hydroxide ions increase, hydrogen ions decrease. Okay. So when you look at the scale, let's just add another page. When you look at your pH scale, if you have something that is a pH of 4 and something that's a pH of 2, 2 will have greater hydrogen ions than 4. If you look at something that is a pH of 8 or 9 and something that's a pH of 13, 9 will have greater hydroxide ions than 9. So acidic has more hydrogen than hydroxide. Basic has more hydroxide than hydrogen. Okay, so let's look at this scale. If 7 is neutral, 7 is neutral. You see at 7, we see distilled water. When we go downwards this way, we could become more acidic. So urine is not as acidic as black coffee, not as acidic as tomato juice. Tomato juice is more acidic than black coffee. Black coffee is less acidic than tomato juice. Gastric acid right here, which is found in your stomach, is extremely acidic. It is a hydrochloric acid, very acidic. As you go upwards, you become more basic. So bleach is very basic compared to baking soda. All right. Now let's add some more back to the scale. We'll just add another scale. It's easier that way. The closer you are to 14, the more you're in right here and right here. These are going to be your strong acids, and this is a strong base. Right here, closer to 7, on either side, is going to be weak acid and weak base. Oh, okay. All right. So if I'm making something more acidic, I am literally just adding hydrogen ions. And I'm doing that by adding acid. And what will happen, like HCl right here, your hydrogens and your chlorines are going to break apart and you're going to add hydrogen ions to solution. If I want to make something more basic, I'm going to add hydroxide ions, and I'm going to add a base like sodium hydroxide that's going to break into hydroxide ions. Changes in pH are extremely important because pH is one of those things that we want to keep constant through homeostasis. If pH becomes too acidic or too basic, it can disrupt protein function, and it can also break apart those lipid membranes. And if our proteins aren't functioning, then the majority of our body is not functioning, because proteins are extremely important when it comes to structures, when it comes to transport within cells. So our body will buffer pHs in order to help decrease a change. So a buffer is something that helps to decrease changes in pHs. So a weak acid is going to be an example of a buffer. A weak base is going to be an example of a buffer. And it's going to help to decrease the amount of change. So where do we see this within our body? Our stomach pH is around 2. After our food leaves our stomach, it goes to the small intestine. The small intestine does not have the protective mucus in place that the stomach has. The stomach has a pH of 2. It has protective mucus to help keep that digestive juices from eating holes in it. The small intestine doesn't have that. So as the food, or at this point it's called chyme, moves into the small intestine, the small intestine will add buffers to that solution to help to bring the pH back to a more neutral level, so that the food, the chyme, does not actually eat a hole in the small intestine. Another example of pH in living systems is acid rain. Acid rain can have effect on communities. It can have effect on plant communities. So if the rain is too acidic, the plants aren't going to be able to grow and function correctly. If plants aren't growing, herbivores can't eat them, or will run out of food, and it can affect the community at multiple levels. So that's one of the reasons why there's concern about the sulfuric output of industry, is because we don't want to change the pH of our condensation. All right, so we're going to take a break here because this is already very, very long. We'll come back and have another